Quantum computing refers to the use of quantum mechanics to run calculations. Quantum computing can run multiple processes at once by using quantum bits, unlike binary bits which power traditional computing. Potential applications. Cryptography. A notable application of quantum computation is for attacks on cryptographic systems that are currently in use. Integer factorization, which underpins the security of public key cryptographic systems, is believed to be computationally infeasible with an ordinary computer for large integers if they are the product of few prime numbers, for example, products of two 300-digit primes. By comparison, a quantum computer could efficiently solve this problem using Shor's algorithm to find its factors. This ability would allow a quantum computer to break many of the cryptographic systems in use today, in the sense that there would be a polynomial time, in the number of digits of the integer, algorithm for solving the problem. In particular, most of the popular public key ciphers are based on the difficulty of factoring integers or the discrete logarithm problem, both of which can be solved by Shor's algorithm. In particular, the RSA, Diffie-Hellman, and elliptic curve Diffie-Hellman algorithms could be broken. These are used to protect secure web pages, encrypted email, and many other types of data. Breaking these would have significant ramifications for electronic privacy and security. Search problems. The most well-known example of a problem admitting a polynomial quantum speedup is unstructured search, finding a marked item out of a list of \n items in a database. This can be solved by Grover's algorithm using \o\sqrt no\sqrt queries to the database, quadratically fewer than the \omega n queries required for classical algorithms. In this case, the advantage is not only provable but also optimal. It has been shown that Grover's algorithm gives the maximal possible probability of finding the desired element for any number of oracle lookups. Problems that can be efficiently addressed with Grover's algorithm have the following properties. 3738. There is no searchable structure in the collection of possible answers. The number of possible answers to check is the same as the number of inputs to the algorithm, and there exists a Boolean function that evaluates each input and determines whether it is the correct answer. For problems with all these properties, the running time of Grover's algorithm on a quantum computer scales as the S. Machine Learning main article. Quantum computers can produce outputs that classical computers cannot produce efficiently, and since quantum computation is fundamentally linear algebraic, some express hope in developing quantum algorithms that can speed up machine learning tasks. For example, the quantum algorithm for linear systems of equations, or HHL algorithm, named after its discoverers Harrow, Hasselbalch, and Lloyd, is believed to provide speed up over classical counterparts. Some research groups have recently explored the use of quantum annealing hardware for training Boltzmann machines and deep neural networks. Computational biology, quantum machine learning. In the field of computational biology, quantum computing has played a big role in solving many biological problems. One of the well-known examples would be in computational genomics and how computing has drastically reduced the time to sequence a human genome. Given how computational biology is using generic data modeling and storage, its applications to computational biology are expected to arise as well. Computer-aided drug design and generative chemistry. Quantum machine learning deep generative chemistry models emerge as powerful tools to expedite drug discovery. However, the immense size and complexity of the structural space of all possible drug-like molecules pose significant obstacles, which could be overcome in the future by quantum computers. Quantum computers are naturally good for solving complex quantum many-body problems and thus may be instrumental in applications involving quantum chemistry. Therefore, one can expect that quantum-enhanced generative models including quantum GANs may eventually be developed into ultimate generative chemistry algorithms. Hybrid architectures combining quantum computers with deep classical networks, such as quantum variational autoencoders, can already be trained on commercially available annealers and used to generate novel drug-like molecular structures.